An imaginary number is a real number times the imaginary unit I. This imaginary unit I is a solution to the equation z squared plus 1 equal to 0, or in an easier way, I squared is equal to minus 1. By the combination of real and imaginary numbers, we can create complex numbers. Where real numbers are represented on the real axis, the complex numbers can be represented on the plane, the complex plane. This plane is made of the intersection of the real axis and the imaginary axis at the point 0 plus 0 times I, which is the origin of this plane. Complex numbers are spotted with coordinates made with their real part and their imaginary part on this plane. So the point Z is equal to A plus I times B.
At the 6th century, Jerome Cardan encountered a problem in the resolution of third-degree polynomials equation. He knew that for the equation x squared minus 15x equals 4, one of the solutions was x1 equals 4. But he also had a formula which gives the value of x, which also means that 4 should be equal to that formula. However, the problem is here there is a square root of a negative number, but the square root of a negative number simply does not exist. So he put this type of equation under the state of causus irreductibilis, the irreducible case, like impossible things to resolve. More than a century after, the imaginary solutions were created by the French mathematician René Descartes, and they are basically correct mathematical solutions, but they are only virtual. After this, Leonard Euler found that all those imaginary solutions can be written as a multiple of the square root of minus 1, and he named this number I for imaginary. Then, with the work of Caspar Russell, the imaginary and complex number will finally have a geometric explanation. They can be placed in a plane, the complex plane, with the Euler's formula appears. Exponential yp plus 1 equals 0.
Fractals are geometrical objects which are made of themselves. They have a similar structure at all scales. It means that fractals have a structure which is made of this structure, and this to the infinity. So, you can zoom to the infinities of structures and you will always find the same structure again and again. There are many examples in nature. There is a Romanesque broccoli. It has a central spike which is made of spikes which are made of spikes again and again. Or, for example, there is the fern, which its leaves are made of fur, and etc. The concept of fractal is recent. It has only been discovered at the end of the 19th century with the Koch snowflakes and the Sierpinski quartet.
Due to its use, we discover more and more uses to this concept, which is everywhere in nature. So it can be used in volcanology, astronomy, biology, economy, art, and more and more. To resume, there is many science domains which can be applied. One of the most interesting one, however, is in the medicine. Fractals could be used to describe the structure of many parts of the body, such as lung or veins, or they also could be used to analyze the heartbeat to prevent from disease or to notice some anomalies.
The mathematician Gaston Julia studied the fractal made from complex sequences which lead to the creation of the Julia set. Fractals can be created with complex sequences applied to every point of the complex plane. The principle of those complex sequences is simple. You have a complex sequence formula and each point has the same complex sequence formula, but the first term is the complex value of this point. And then, for each point, you make its sequence tend towards the infinity. Finally, if the sequence is bounded, you color this point in a color often in black, and if it's not, you color this point with a different color. Often the color depends on the time taken by the sequence to diverge. Finally, the sequence in the Julia set are polynomial equation. For example, z of n is equal to the square of z of n minus 1 minus 1.25, where z of 0 is the complex value of each point of the complex plane.
In 1975, Benoit Mandelbrot studied fractals made from complex sequences and created the Mandelbrot set, which act like a mapping of the Julia set. So, in this case, C is equal to the complex value of the point taken.